Alright, so we're going to do some stoichiometry, and basically what this means in this chapter is that we're introducing 3 new conversion factors, and we're going to use them exactly how we use conversion factors in the first chapter. Okay, the 3 conversion factors are Avogadro's number, which states that 1 mole is equal to 6.2 times 10 to the 23rd items, whatever those items are, atoms, molecules, whatever that happens to be. We'll then look at molar mass, which is always with units of grams over mole. And some people like putting 1 mole in there to remember that there's only 1 mole. And then we'll be talking about molar ratios. So we'll see how many we can get to in this video. Now, we're going to work some problems using these concepts. We've already introduced those concepts in the slides. So now we're going to start with Avogadro's number. And remember, Avogadro's number is that equality, so we can make it into a conversion factor by putting one over the other, and it can be in either direction, depending upon what we need for the problem. So let's go ahead and answer this next question using that conversion factor. It asks for, what are the number of atoms of copper in 0.5 moles of copper? Now, with any word problem, I'm going to pull the information out of the problem before we begin. So we want the number of atoms, and specifically the number of copper atoms. And we have 0.500 moles of copper. All right. So now we've pulled that information out. We don't have all the words of the problem. We can actually work with the numbers. Well, we're going to start with a thing that's not the conversion factor. So we're going to start with the thing that it starts out in the number. So we're going to start with that 0.500 moles of copper. We're going to put our grid up so that we keep track of everything in the numerator and everything in the denominator. And we're going to use, we already said we're going to use our Avogadro's number. Whenever you have atoms to moles or molecules to moles, you know that that should trigger an idea that that's Avogadro's number that you're going to need. Okay? So moles are on the top. Where do moles have to be to cancel out? Well, they have to be on the bottom. So we're going to stick the moles in the bottom, and according to our Avogadro's number, that's 1 mole. And the thing on the other side, we're going to put on the other side of the line. So 6.02 times 10 to the 22nd items. In this case, we're talking about atoms. So we check our units. Our units are going to cancel out. Moles on the bottom, moles on top. The only units we haven't canceled out are atoms. So that's what our answer is going to be. Now we go ahead and do the math. We plug in 0.500 times 6.02 EE to the 23rd. And that's how my calculator works. Remember, different scientific calculators work slightly differently. So you want to make sure that you know how to use your particular scientific calculator. We get 3.01 times 10 to the 23rd. Now sometimes on these calculators, the 23rd can be far over to the right, so don't forget to get that exponent written down in your final answer. Now, what do we do before we move on to the next problem? Significant figures, always significant figures. So we've got one, let me draw the arrows there, 2, 3 significant figures in this number here. 1 mole is an exact number, so we're not going to worry about significant figures there. We've got 3 significant figures here, so our answer needs 3 significant figures. And we double check it, 1, 2, 3. In fact, our answer, as written, has 3 significant figures, so we're all good. Now, we're going to move on and talk about molar mass next. Now, to understand molar mass, we need to come back and talk about another concept first, which is formula mass. So formula mass is just taking up the masses of all the atoms in the compound and then getting a mass of the whole compound. So let's look at the formula mass of H2SO4. Well, on our periodic table, we want to make sure we have our periodic table. We know that H has a mass of 1.01. Remember, we're going to use it to the second decimal point, the hundredths place. In this class, we will round all of our masses from our periodic table to the hundredths place. We want to make sure we go that far. Sulfur from the periodic table, we can look up, and it's over here. It's 32.07, because we're rounding there. And oxygen is 16.00 when we round that. And remember, on the periodic table, these are AMUs, atomic mass units, because one hydrogen is really, really small. So it's an atomic mass unit. So if we want to do formula mass, or could be termed formula weight, what we're going to do is we're just going to add these up. We have 2 hydrogens, so we're going to have 2 of the 1.01 AMUs. And then we're going to add, we've got 1 sulfur, so we're going to add the 32.07 AMUs. And then we're going to add, we've got 4 of the oxygens, so 4 times the 16.00. All right, we get our calculator out and we type that all in. And we should get 98.09 AMUs. Don't forget, the unit when you're talking about individual atoms is always AMUs because they're really, really small. So one molecule of H2SO4 has the mass of 98.09 AMUs. Now, because of the way we define what a mole is, we can actually benefit from this because this number of AMUs equals our molar mass. So if H2SO4 is 98.09 AMUs, then its molar mass is 89.09 grams per mole. So 1 mole of H2SO4 will weigh 98.09 grams. It's the same number, right? The only difference is the units that we put here. Here we're talking about it on a microscopic scale. We're talking about atoms and 1 molecule of H2SO4. Here we're talking on it the macroscopic scale. We're talking about a whole mole of these H2SO4 molecules. Okay? So the process to get the molar mass is the same as the process up here. We just add up the individual ones, but the units become grams per mole when we're talking about molar mass. Well, grams per mole, that's one thing over another thing. That should look like a conversion factor, right? And we can use it this way, or we can flip it. So if we need to, we can write moles per 98.09 grams. Now, one thing I want you to be very clear on, it's always per 1 mole. It doesn't matter how many moles of a compound you have in your actual problem, it's always per 1 mole. If it is helpful to write the 1 in there, to make sure that you keep in mind it's always per 1 mole, go ahead and write it in. It's not going to change your math any. But I've had students write the grams, and then they try to write the number of moles in the problem there instead of 1 mole, and that'll make the problem wrong. So do watch that. It's always per 1 mole. All right, so let's do some problems using this idea of a molar mass. Let's do a problem where it asks for the number of moles of water in 36.0 grams of water. Okay. So first of all, I'm going to pull things out of all the words. So we're looking for how many moles of H2O. That's what we're looking for. The other thing that we're given is that we start off with 36.0 grams of H2O. Okay. Now that we've got everything pulled out from all the words, we can deal with just the numbers, and we can think about how we're going to do this. Whenever you want to go grams to moles or moles to grams, That's a key that you're going to be using, that molar mass as a conversion factor. Okay? So we are going to need the molar mass of water. Not a problem. We can do that little calculation over here at the side. We have 2 of the 1.01 hydrogens, and we have 1 of the oxygen, which is 16.00. We're going to add those up, and we get 18.02 grams per mole. And remember, grams per 1 mole. Doesn't matter how many moles are in the problem, it's always grams per 1 mole if you're dealing with molar masses. Alright, so now we've got this conversion factor, we can actually use it over here. Here we've got grams in the top, so where do grams have to be to cancel out? Well, they have to be in the bottom. So we're going to put our grams in the bottom so they cancel out. And in this case, we got 18.02. So we're going to write that 18.02 in there. And whatever's on the other side of the line here, we're going to put on the other side of the line there, 1 mole. Now our grams are going to cancel out. And what we have left in units here is moles. It's the only thing we didn't cancel out. So let's go ahead and get our calculator. And we'll do our 36.0 divided by 18.02, excuse me. And the answer we get, let me just make sure I did that correctly. My calculator's going crazy here. There we go. The answer I get from the calculator is 1.99778, and it continues on. So what is the one thing we've got to do when we finish every problem before we move on to the next one? We have to look at significant figures. So let's go ahead and do that. This one has 3 significant figures. 1, 2, 3. The mole is an exact number, and here we've got 4 significant figures. So what's the smallest, 3 or 4? 3 is the smallest. So the answer has to have 3 significant figures. So this is not our final answer. We need to go 3 significant figures. Here's 1, here's 2, here's 3. We go next door and see if we have how to round it. This is above 5, so we have to round up. So the 199 has to go to 2. 2.00, because we still need those 3 significant figures, moles. That is our final answer. Okay. Let's see if we have time for one more problem here. There are times when we're going to want to combine these 2 sets of units, these 2 conversion factors, where we've got moles and atoms, or moles and molecules, and we need grams in there too. So we can actually stack our conversion factors, put more than one in a problem. So let's look at this one. It asks for what is the mass of 1 atom of copper in grams. Okay. So we're going to start off with the thing that they give us. We want grams, and the thing that they start off with is 1 atom of copper. Okay. So if you've got grams and atoms, well, the only conversion factor that really involves atoms is Avogadro's number. So we can change atoms to moles using Avogadro's number. Okay, this is sort of our logic that we're putting up here. Then we can change moles to grams with our molar mass. So let's go ahead and do that. Avogadro's number we said was first. We got atoms in the top, so atoms have to be in the bottom to cancel out. 6.02 times 10 to the 23rd atoms in 1 mole. And then the molar mass of copper, we can look it up in our periodic table. It is 63.55 grams per mole. Moles in top, so moles have to be in the bottom to cancel out. Moles down here, the number on the other side of the line goes on the other side of the line. Now we cancel out our units. The only units we didn't cancel out are grams. And we go ahead and do that math, and we get